You know that feeling, right? You're gathering all this data, logs, sales numbers, maybe sensor feeds, and you think, great, let's chuck it all in a data lake. Super flexible, scalable, cheap storage. Sounds perfect.
Yeah, sounds perfect until it doesn't. Suddenly it's less like a pristine lake and more like a murky swamp.
Exactly. A swamp where you're not sure about the data quality, finding the right version is, well, a pain.
And trying to reliably update or delete anything. Forget about it. It's that classic problem, isn't it? Getting cloud scale
Okay.
without sacrificing the kind of reliability you'd expect from a proper database.
Totally. And that messy, unreliable swamp, that's exactly what we're diving into today. We're going deep on Databricks Delta Lake. It's tech designed specifically to some order, some structure, some reliability back to those huge data lakes.
Right. So based on the material you shared, our plan is to really unpack what Delta Lake actually is,
Yeah.
how it tackles those classic data lake headaches, explore its really powerful features. We'll also touch on how it fits in the broader picture, compared to other approaches, and even share some real-world battle scars, I guess, insights from running it at serious scale.
Consider this your guide to the core ideas that make Delta Lake so foundational for, like, the modern Databricks Lakehouse. So let's get grounded first.
Okay, setting the stage. First off, Databricks itself, what is it? Well, at its core, it's a big data analytics platform built around Apache Spark, offered as a managed service in the cloud. Importantly, it was founded by the folks who originally created Spark, so they know it inside out. It's meant to be a unified place for data, analytics, AI, the whole shebang.
And their story is really tied up with how data lakes evolved, isn't it? We remember traditional data warehouses kind of rigid, mostly for structured data. The data lake was a big reaction. Dump everything in. Structured, unstructured, semi-structured. Logs, images, JSON, all of it.
Yeah, the idea was scale and flexibility on cheap cloud storage. Democratize the data. But like you said, with the swamp analogy, that flexibility had some serious downsides. The sources are pretty clear on this. That lack of built-in structure, it often meant data quality just tanked. It was too easy to just throw stuff in,
Yeah.
which led to duplicates, inconsistencies, basically garbage in, garbage out, but like at massive scale.
And the big one, reliability. Traditional data lakes just didn't have those guarantees you get with databases. No guarantees about reading data consistently while someone else is writing, no strong durability promises. And things like built-in versioning or auditing or easily rolling back, nope, not there.
And that is the void Delta Lake was designed to fill.
Okay, so lay it out for us. What is Delta Lake fundamentally?
So Delta Lake is described as an open source optimized storage layer. The key thing is it's built on top of your existing data lake storage. Those files sitting in AWS S3, Azure Data Lake Storage, Google Cloud Storage. It worked by taking the standard Parquet data files you're probably already using and adding a transaction log alongside them.
Ah, so it's not replacing my storage, it's adding a management layer to it.
Exactly. Its main job is to bring database-like reliability, performance, and governance to the huge scale of data lakes. It's actually the default format for tables inside Databricks now. It turns that messy collection of files into a proper, robust table you can query.
Got it. How does it pull that off? What are the main pieces?
Okay, first you have the Delta tables themselves. The sources call them mega-sized spreadsheets optimized for large-scale analysis, which I kind of like. They store your actual data, column by column, in that efficient Parquet format. But the crucial difference is these tables are transactional. Every single change, every operation is treated like a database transaction.
Okay, transactional. And these transactions, they get recorded somewhere.
Yep. In the Delta log, usually it's a little directory called Delta log sitting right next to your data files. Think of it like the table's digital ledger. Its system of record, its source of truth. Every single transaction, adding files, removing files, changing the schema, whatever gets logged, in order, usually as small JSON files. And over time, because that log can get huge, Delta Lake creates checkpoints, basically consolidated summaries of the log to speed things up.
So the log is the brain, the central coordinator. It knows exactly which Parquet files make up the table at any given point in time, and the actual data files just sit in your cloud storage, but the log points to the right ones.
You got it. And it's this super detailed transaction log that lets Delta Lake bring AC guarantees to your data lake. Atomicity, consistency, isolation, and durability.
Okay, ACD. Let's break that down, because this is the core of the reliability promise, right? Atomicity first.
Atomicity means all or nothing. Simple as that. A transaction either fully completes, gets committed to the log, or it fails completely. It leaves the table exactly as it was before, no half-finished changes. The source material had a good example. You try to insert, say, 1,000 records. One record fails a schema check, boom. The entire batch of 1,000 is rolled back. None get inserted.
Wow, okay. That immediately solves a huge data lake headache, those partially loaded, inconsistent batches.
Right.
What about consistency?
Consistency ensures that every transaction takes the table from one valid state to another valid state. It follows predefined rules. Schema enforcement is a big part of this. Delta Lake checks if the data you're trying to write actually matches the table's schema before it commits. So you can't accidentally shove strings into integer columns or add unexpected columns and mess up the table structure.
Like a bouncer checking IDs at the door for your data. Okay. Isolation. How does it handle lots of people trying to read and write at the same time?
Right, isolation. This lets multiple operations happen concurrently without messing each other up. Delta Lake uses something called optimistic concurrency control. So instead of locking the whole table when someone writes, which would kill performance at scale, it lets multiple operations go ahead. It only checks for conflicts right at the very end, at commit time. If two operations happen to try and change the same file simultaneously, the log helps detect that. One succeeds, the other fails gracefully and can be retried.
Ah, so it's optimistic. It assumes conflicts are rare and handles them efficiently when they do happen. Makes sense.
And durability.
Durability is the guarantee that once a transaction is successfully committed and written to that Delta log, the change is permanent. It's safe. It's written to your persistent cloud storage. Even if, like, the whole cluster crashes right after the commit, the change recorded in the log pointing to the new data files is still there. So, that transaction log, it's the secret sauce. It layers that robust database-like reliability onto plain old cloud storage. That clicks. Now, with that foundation, what kind of cool features does this unlock? What can you do with Delta Lake?
Well, a really fundamental one is schema enforcement and evolution. We touched on enforcement for consistency. It stops bad data getting in, like trying to write text into a number column. Delta Lake will throw an error.
Okay, but schemas aren't static, right? You often need to add new columns later.
Exactly, and Delta Lake handles that pretty smoothly with schema evolution. You can add new columns or make other kinds of changes that don't break existing data without needing to rewrite the whole massive table. Usually you just flick a switch, like using an option called merge schema when you write, or setting a table property. It's worth noting, though, changing the type of an existing column is harder. You might need overgrid schema for that, but adding columns, pretty straightforward.
Nice. Flexibility to adapt. What about actually working with the data in the table? Inserts, updates?
Yeah, this is where it feels really familiar if you've ever worked with a SQL database.
Yeah.
Delta Lake supports all the standard DML commands: select, insert, update, delete. And also the DDL stuff like create table, drop table, alter table. It speaks SQL.
And the sources really highlight one command, merge. Why is that so important?
Oh, merges. Well, it's probably the workhorse for most data pipelines using Delta. It lets you combine inserts, updates, and even deletes into a single atomic operation based on whether rows match between your source and target. It's perfect for upserts. Update the record if it exists, insert it if it's new, all in one go.
Ah, I can see how that simplifies things massively, especially for loading changes. No more complicated multi-step logic. Just merge. Speaking of changes, this reliability also enables stuff like data versioning and time travel, doesn't it?
Yes, and this is like truly mind-blowing when you first see it, because every single write operation creates a transaction recorded in the log. Delta Lake automatically versions your table history. Every commit gets a version number. And time travel is the feature that lets you query the table not just as it is right now, but as it was at any specific point in the past. You can query version as of some number or timestamp as of a specific date and time.
Wait, hang on. So if I run a bad update, mess up a million rows, I can just query the table as it was 5 minutes ago before I messed up.
Absolutely. Or query yesterday's version to regenerate an old report exactly. Or even restore the entire table back to that older good state. It works because Delta Lake doesn't immediately delete the old data files when you update or delete rows. The log just stops pointing to them for the latest version. But those older parquet files are still there, linked to the older versions in the log. For a while, anyway.
That seems incredibly powerful for audits, debugging, fixing mistakes. Wow.
Yeah.
But holding on to all those old files, doesn't that eventually cause problems like storage costs or maybe performance?
It definitely can, especially if you're writing frequently. You can run into the small files problem.
Yeah.
If you're constantly adding small batches of data or streaming data in, you can end up with thousands, maybe millions, of tiny little parquet files. And query engines like Spark, they really struggle with that. Opening tons of tiny files is way less efficient than reading fewer larger ones.
Okay, that makes sense. So how do you fix that mess?
The main tool in your belt is the optimize command. What Optimize does is it reads a bunch of those small files and rewrites them into fewer, larger, more optimally sized files. This can give you a huge boost in read performance.
Right. And I've seen Zorter by Y mentioned alongside Optimize. What's that about?
Ah, Zorter. You use that together with Optimize. It's an extra technique. It's really good for columns you filter on a lot, especially columns with lots of unique values like maybe a user ID or something. What Zorter does is it physically rearranges the data within those newly optimized files, trying to group rows with similar values in your Zorter columns together. This lets the query engine do much better data skipping. You can look at the stats for a file and say, nope, the value I need isn't in this file at all, and just skip reading it entirely. Big speed for queries with filters.
Okay, so Optimize fixes the file size problem. Zorter arranges the data inside the files to make filters faster. Got it. Now, about those old files that time travel needs. They can't just hang around forever, can they? Storage costs would explode.
Correct, they don't. That's where VacuUM comes in. And this one's really important for cost management. VacuU is the command that actually permanently deletes the underlying data files that are no longer needed by any current version in the Delta log and are older than a certain retention period. The default retention is usually 7 days.
Permanently deletes. Okay, that sounds slightly terrifying. Is there like a safety switch?
Yes, and this is super important advice from the sources. Always run VacuUM DRI run first. Seriously, DRI run will show you exactly which files it plans to delete without actually touching them, because once you run the real VCUM, those files are gone, poof, and you lose the ability to time travel back to versions older than your retention periods. So you need to be deliberate about it.
Okay, good tip. DUI run first, always. The sources also hinted there might be even more advanced ways to optimize beyond Optimize and Zorter.
Yeah, there are a few other things. Traditional partitioning, dividing your data into folders based on low cardinality columns like date or region, that's still sometimes useful. Then there are things like balloon filters, which can speed up lookups on columns with very high cardinality, like unique IDs or maybe text fields.
Ah,
And then there's a newer thing called liquid clustering.
liquid clustering. How's that different from, say, Zorter?
So liquid clustering is designed to be a bit more, liquid, more adaptive and incremental. Unlike Zorter, which often forces a big rewrite of data and is tied to specific columns you choose up front, liquid clustering aims to continuously optimize the data layout and file sizes as new data comes in or gets modified. The goal is to reach a stable, optimized state more naturally, and it also makes it easier to change which columns you want to cluster by later on without another massive rewrite. It's sort of trying to automate more of that optimization burden.
That sounds potentially much simpler to manage long term. Okay. Any other, advanced capabilities we should know about?
Change data feed, or CDF, is a pretty big one. So remember, the Delta log tracks changes at the file level, like which files were added or removed in a transaction. CDF goes deeper. It tracks changes at the row level. It records the actual inserts, updates, and deletes that happen to individual rows within those files.
And why would you need that level of detail? What's the use case?
Oh, it's super useful for building efficient downstream pipelines. Instead of reprocessing everything, you could just query the CDF to see exactly which rows changed between version X and version Y. It makes incremental processing much easier and more accurate. It's also great for really detailed audit trails. Who changed what, when.
Gotcha. Delta log equals file state. CDF equals row change history. Clear.
No.
What about just making copies of tables?
Yeah, Delta Lake has cloning. Two main flavors. There's shallow clone. This just copies the metadata, the Delta log basically, but it points back to the original table's data files. It's super fast and cheap to create, great for dev test maybe, but it's fragile. If the original table's data files get VCU med away, the shallow clone breaks.
Right, because it doesn't have its own copy of the data. What's the alternative?
Deep clone. This copies everything, the metadata and all the data files. Takes longer, uses more storage, obviously, but you get a completely independent, self-contained snapshot of the table at that point in time, safe from changes to the original.
Okay, so shallow for quick tests, deep for real backups or independent work streams. Makes sense. And one last cool thing mentioned was delta sharing.
Yeah, delta sharing is pretty neat. It's an open protocol that Databricks developed. It lets you securely share specific delta tables or slices of them with other people or organizations, even if they aren't on Databricks or even in the same cloud. And crucially, you share access without having to physically copy or replicate the data all over the place. They query your shared data directly under your governance.
Wow, that sounds huge for collaboration or building data marketplaces. Very cool. Okay, so we've got a good handle on the tech now, from the basics to the advanced stuff. Where does this whole Delta Lake-powered approach, what Databricks calls the Lakehouse, fit in the bigger picture? How does it compare to, say, a more traditional cloud data warehouse like Snowflake?
Right, the ecosystem view. The sources draw some distinctions. The Databricks Lakehouse, built on Delta Lake, is fundamentally a platform as a service, a pay-as. It runs on your cloud storage, your S3 buckets, your ADLS account. It's positioned as this unified platform that's strong not just for SQL analytics, but also for machine learning, AI, streaming data, handling all sorts of data types side by side.
Okay, pay us on your storage.
Bro,
And Snowflake.
Snowflake is generally seen more as software as a service. SaaS, it kind of manages its own optimized storage layer for you behind the scenes. Historically, its huge strength has been as a super polished cloud data warehouse, really focused on structured and semi-structured data for BI and SQL workloads. So while both are incredibly powerful cloud data platforms, they come at it differently. Delta Lake means the core data layer lives in your cloud account, under your direct control. Snowflake abstracts that away more.
Interesting. It feels like maybe one evolved from the data lake, adding structure and governance, and the other evolved from the data warehouse, adding flexibility and scale. Maybe meeting in the middle on many use cases, but with different philosophies underneath.
That's a really good way to put it, actually. Different origins, different design centers. And, finally, let's bring it back down to earth. What are the real-world lessons? What happens when you're not just talking terabytes, but like petabytes? Billions and billions of records.
Yeah, the sources had some pretty honest takes on this.
They did. First big takeaway. Doing this at scale needs serious upfront planning. It's not just flicking a switch. You got to think about the architecture, how you design your schemas, setting up permissions properly, having solid dev test prod environments, the whole setup.
And I bet cost becomes a huge factor at that level.
Oh, absolutely. Understanding the cost difference between running interactive notebooks versus optimized scheduled jobs. Crucial for managing the bills. And like we talked about, that maintenance running optimized regularly using VaceUM carefully. It's not optional. It's essential. If you skip it, performance will degrade, costs will climb. It'll bite you eventually.
So the power comes with responsibility. You need to actively manage it.
Yeah, you do. And it means having at least some grasp of basic Spark tuning concepts, understanding how Delta interacts with Spark, and just being ready for operational stuff. Like, how do you handle massive numbers of concurrent writes smoothly? What happens if your cloud provider has instance availability hiccups during peak load? Oh, and having a solid data quality plan right from the start. Non-negotiable. Don't wait until it's a mess.
Okay, so it sounds like Delta Lake is incredibly powerful, definitely a big leap forward from older tech, but it's not quite set it and forget its magic, especially when you're really pushing the limits of scale.
That's exactly the balance, I think. The sources acknowledge the challenges, but they still call Databricks and Delta Lake a game changer. And it is. The ability to handle those huge volumes with things like merge, simplifying complex logic, it's way easier than the old Hadoop days, for sure. Spark became much more accessible. But the warning is clear. Just because it's easier to get started doesn't mean you can skip the homework. Planning, understanding the internals, committing to the operational discipline, that's what separates success from failure at scale.
That feels like a really solid place to wrap up our deep dive on Databricks Delta Lake.
Yeah, we covered a lot, from the data swamp problem to how Delta Lake brings reliability with the transaction log and asset guarantees. We explored features like time travel, schema evolution, merge, change data feed, and the crucial maintenance like optimize and vacuum, plus newer ideas like liquid clustering.
And it's clear, right? Delta Lake really is this foundational piece trying to give you the best of both worlds. Database reliability on data lake scale, enabling that whole lakehouse vision for everything from BI to AI.
Absolutely. Yeah. But the key takeaway, especially from the real-world perspective, is that while it unlocks amazing capabilities and simplifies a lot, getting the most out of it, particularly at scale, really demands that thoughtful design, understanding the mechanics, doing the maintenance, and focusing on data quality. It's a sophisticated tool, and you get out what you put in.
So maybe something for you to think about as you navigate your own data challenges. With platforms like Databricks evolving so fast, we mentioned things like predictive optimization, liquid clustering getting smarter. How is that balance going to shift? The balance between fully automated, managed platforms and the need for deep, hands-on expertise and configuration. What skills become most critical as these tools get even more powerful and maybe more complex under the hood? Something to ponder.